So I'm going to get started. Good morning and welcome to the October 2022 meeting of the California Society for Healthcare Engineering Los Angeles chapter. I am Phil Harrigan, the Vice President of the LA chapter, and our President, Tom Peterson, and our Vice President, Brian Guerrero, are not able to be with us this morning, so you're going to have to put up with me. In the background and controlling virtually everything is Beth Demeter from CSHE. And this meeting is being held in person at the new Elysian facility in Diamond Bar and live over Zoom. It is being recorded and will be available later on the CSHE website. Our see here. Yes. Our educational presentation today is a simplified assessment of the risk of infection-bound, of aerosol-bound viruses in ventilated rooms, presented by Chris Lawrence, Vice President, HVAC Sales at LTG AirTech Systems. This is a very timely subject as COVID continues to plague us, despite what you may have heard. Before we get into that, I'd like to thank Kevin Whitney and Elysian for having us here today at their new facility. I was at their previous facility on the other side of this business park many times to do training on locks. I still carry the screwdriver you guys gave me when I took mortise case training for, and I love it because it's got a number 3 Phillips tip, so we don't screw up the hinge screws. I am the facility locksmith, among other things, at Providence St. John's Hospital in Santa Monica. Elysian also provides a lot of online training. In fact, there is one going on right now, and there's another today at 11 a.m. on the essentials of access control. I really like their online training, and I particularly like my favorite blog, I Dig Hardware, done by Lori Green. She's been blogging for Elysian for years and deals with all issues related to locks, doors, access control, and egress. If you have any questions about codes in these areas, Lori Green is a terrific resource. And I hope to have her out here to present for us in person sometime next year. And you can see she also provides innovative solutions to tough door problems. Okay, and finally, I want to thank Westcom for providing breakfast this morning. And all of our gold and silver sponsors whose support for CSHE allows us to continue to be the conduit for professional growth in the operation of the built environment in healthcare in California. These are our gold sponsors, including, of course, Westcom. Is there anybody here today from Prevent or let's see, Prevent or Fire Door Solutions? Because I understand that Prevent and Fire Door Solutions, which are both gold sponsors for us, have merged and are now remediating. And these are our silver sponsors. Thank you so very much for your continuing support. Okay, now, normally at this time in the meeting, I'd go around the room and have everyone introduce themselves, but unfortunately, our Zoom technology is not set up for that yet. So we'll put that off for later. Now we're going to, let me bring on our main act, Chris Lawrence here. for his educational presentation. Chris has flown all the way out from South Carolina, is it?
Georgia.
Georgia,
You will.
to be with us today. Thank you so much. I can't believe you did that. His work has predominantly focused on low energy hydronic solutions, including decentralized ventilation, fan coils, chilled beams, radiant panels, sails, and UV recirculation for COVID disinfectant. Chris is based in Athens, Georgia, where he lives with his wife, daughter, and son. He graduated with a degree in mechanical and production engineering and furthered his studies in business management at Cranfield University in England. He transferred to the US in 2004 and became a US citizen in 2011. Chris has spent the past 3 years working for LTG Incorporated, pioneering their UV stereoventilation for disinfectant of airborne viruses. Prior to that, he spent 35 years with Trox. He's worked on thousands of buildings in Europe, the Middle East, Asia, and the United States. He has 43 years experience in the selection and application of HVAC products such as air distribution, attenuation, VAV, CAV, filtration, air control and isolation, and nuclear HVAC. As we continue to fight to overcome COVID-19, Chris has focused on solutions that either provide us more outside air or disinfect airborne viruses using recirculation and UVC. Please welcome Chris Lawrence.
Hello. Thank you. I have to do a little bit of housekeeping while we swap the slides over. As you can tell from my accent, I'm not from California. And sometimes I'm described as a little bit irreverent when I do my presentation. So I'd just like to apologize to everybody now. If I say something that offends you, I'm kind of sorry. But it's just my approach, just the way I do things. I find fun in everything. So everything I like to do, I try and bring a little bit of it as well. If we have any questions, please ask them as we go along. Today I'm with Humera. She's from Toro Air, and they are actually our rep in Southern California. So what I would say is, if they're really difficult questions, could you aim them at Humera? If they're really simple ones, aim them at me. Please try and not ask the same question twice, because often we make this stuff up as we go along. We might give you a different answer if you ask it a second time. So let me just do the housekeeping. I'm going to turn off the camera. And swap over the screens. Share this one. So, Beth, are you now seeing a presentation, or are you seeing just, so let me share. Where is it there? Share, start. I can now see the presentation, but I can't. Why am I not? Hold on.
What we're still seeing is the edit mode.
Yeah,
That
can you
helps any?
see it? Are you seeing it now?
Perfect. Yes.
Yay! I knew we'd get there. So, as Philip said, this is a presentation on the simplified assessment of the risk of infection by airbound or aerosol-bound viruses in a ventilated room. And then really following on from that, if you like, the correct application of in-room UVC. So just to start off, really, this is the content we're going to go through. So part one is a quick summary of ASHRAE recommendations that were made in 2020. Following on from that, the basis of the analytical tool is based on a white paper that came out of a large university in Germany. Then we're going to define what the limits are in terms of assessing risk. We will look at the parameters of input. So I've actually looked at a 4-room patient room and looked at the effect of catching something while you're in there. We'll go through the examples. We'll go back to the Archon model and how it relates to that example. And then finally, we'll really end up with, have we not increased enough outdoor air, why we should apply UVC and the properties behind that. So let's just move on. Part one, ASHRAE recommendations. So in 2020, they issued a position document. What I tried to do was summarize some of the statements they made within that document. The first one was, well, everybody knows by now we need to increase the outdoor air that we deliver to a space. We're not talking about increasing the total volume of air. All we're saying is that part of it, which is the outside air, the ASHRAE 62 part, should be a higher volume. So I just want to make that clear now. When we say, let's increase the volume we're delivering, we're not increasing the total flow unless it's 100% outside air solution. They also suggest that we fully open outdoor air dampers, even open windows. Well, if any of the maintenance guys on your buildings are like the ones I know, they tend to shut these things down because it reduces energy. We're not pulling in so much 100-degree air in the summer that we have to then cool down. But what we want to do is increase outdoor air delivered to space. We bypass energy recovery systems, those that could transfer nasty particles from the return and exhaust route back into the supply route. And we know that a lot of the energy wheel companies have done a lot of work on their wheels to prevent the migration of particles from one side to the other. They talk about disabling demand control ventilation. And in fact, they went to the nth degree of saying you should even have snorkels and direct exhaust systems over everybody's head. They also want us to keep systems running longer, so a number of hours before people arrive and a number of hours afterwards. The idea is to purge the space, make sure it's clean for the next set of people that move in. And the real problem we have is they've made these recommendations, but they're not telling us how much to increase it by or what the effect is. So we took it a little further. We found a paper that had been published in Germany, which is this University of Aachen white paper. And by the way, everybody that attends, if you contact our friends at Toro Air, they'll give you a copy of the original German paper. It has all the calculations in it. I spent about 9 days of my life trying to translate it back into American English. So you can have a copy of that as well. And all of the software that you see in here, that's also available. So at the end of the day, you don't have to take my opinion. You can actually investigate it and look at it and work your way through all the calculations. So in March 2020, actually a month before the ASHRAE paper, the University of Aachen published this white paper that I believe provided the answer to the question, what's the effectiveness of outside air? Oops, so go. So they based their study on about 100 years of back studies in terms of how airborne viruses are transferred from people to people. They especially looked at the H1N1 outbreak that we had in 2008, 2009, 2010. They looked at how ventilated spaces were being typically used, whether that be a home or a meeting room, an open plan office, lecture hall, exhibit hall. They even looked at traveling from, I think it was Dusseldorf to Berlin, either in a car or in a plane, and then produce a set of data to show how clean or dirty that was. Believe it or not, the aircraft was almost the cleanest. So all of our fears of flying should have gone away. Then they updated their data. They used the current population and the R number. So the R number was how many people does one person infected infect. If that R number is over 1, it's growing. If that R number is less than 1, it's decreasing. So they use that. And they published this paper. As I said, it's a German white paper. It's probably about 15 pages long. There's probably 4 or 5 pages of calculations that they go through everything that they looked at. And what they did is they said, okay, let's identify our risk of catching COVID based on us being in a safe harbor. Their example was a two-person apartment in I think it was Dusseldorf, and the ability of those people to go out and do other things and come back during high infection rates. What was the relative risk to them of them catching COVID or infecting somebody else? They called it the relative risk because ultimately, unless you look at your specific building with your airflow, with your number of people, with your infection rates, it's always going to be a relative number. So we talk about RR infection in comparison to the safe harbor. So what we're really saying is, do I have a higher risk when I leave my home of going to this meeting or going to the office or going to hospital than I do at staying at home? So that's our relative risk in comparison. All we've done is updated it for a typical American home and the peak infection rates that are in this country maybe a year or so ago. If you need the program unlocking so you can put in localized numbers or localized home sizes, that's entirely up to you. So based on the room type, its volume, so how big is it, and the amount of outdoor air that was supplied, and how many people occupy that room and for how long. The length of occupation is a very, very key ingredient. In fact, the amount of outdoor air that you deliver to a room for a 1 hour period is lower than what you need to deliver for a 2 hour period. I don't mean, oh, it's so much CFM per minute. It's typically, if I'm delivering 15 CFM per person for 1 hour a year, if we're staying 2 hours, I probably need to up that to at least 20 CFM per person. It effectively shows us how to make these ventilated rooms have the same risk as the safe harbor, your home location. Everybody following me? Good. So let's just look at safe harbor. In the base model is an average sized home, 4 people in it, and we talked about them being in there when we were kind of under lockdown. So I don't know, there's a mum and dad and 2 youths, and they're spending probably about 14 hours a day at home. They're only going out if they have to, and that's maybe a maximum of 8 hours. We're also assuming that that home has 1 air change of, per hour of infiltration of outside air. There's a lot of our homes these days, we have heating and cooling, but we don't actually have any ventilation. So this assumes that you are mechanically ventilating this space. Opening windows isn't really good enough, depending on the temperature differential, wind direction, etc. You may not get fresh air coming into a space. The infection rates are based on the peak numbers, which was January 2021, as published by the CDC at about 1.75 million cases. And if your room had openable windows and no ventilation, again, we're assuming you're achieving 1 air change rate of outside air. This was some published data of how long you should open a window to ventilate a space. And again, it's based on the month of the year, the temperature differential. It's all a sort of general rule of thumb. Let's open a window and hope for our best. And obviously, if we're dealing with healthcare, we're probably not going to have operable windows anyway. So, in terms of the relative risk of infection factors, we talk about whole numbers. So if we say that you have a relative risk of 2, this means if you come from your home, you come here, and this space has a relative risk of 2, you have twice the chance of catching infection or catching COVID than you did had you stayed at home. If it's 1, it's equal. If it's 0.5, then obviously it's half the risk. And a lot of the healthcare projects we worked on, they actually wanted it to be cleaner, to have half the risk, because what they didn't want is you going there for a sprained wrist and catching COVID while you're actually in the hospital itself. part of what they call infection control. So here are my input parameters. I took a 250 square foot per patient. So this is a four patient room. I used the guides that were on the internet. So they told me 250 square foot per person plus 30 square foot per visitor. So that equaled 4 patients in a 1,240 square foot ward. They're there for 24 hours a day. I worked on them having an outdoor air delivery of 13 CFM per person plus 13 CFM per visitor. So using the maths, when there's only 4 people in there, we're actually delivering 39 CFM per person, because we're doing this as a constant volume system, and therefore the average air change without visitors was 0.6 air changes, quite a low number. We assumed there was 0 infiltration. It was a nice quiet space. There'd be soft furnishings, and we were aiming for a risk factor of 1. We wanted this to be as safe as our safe harbor. And then I said, well, okay, what happens if all the visitors turn up at the same time? So now we've got 12 people in the same space, but instead of them being there for 24 hours, they're there for 8 hours, just as a comparison number. And therefore we're back to this 13 CFM per person average with visitors, and it's still the same air change rate. We haven't varied the volume in the space. So what we then did is we took all the data and turned it into an analytical tool. And this tool is available for you. It's an Excel spreadsheet. I always think Excel spreadsheets are dumb, in so much as if you put dumb in, you get it done out. So I do apologize for that, but it's a very, very simple tool. So here is our reference location. It gives us our floor area, our room height, the fact that there's 4 people there, that they averagely occupy the space for 14 hours. And I said there was 1 air change rate. Here is our infection data. So at the time, 328 million people in the United States, of which 1.75 million were infected. That data is locked in, but as I said, if you want some different data in there, we can open that up for you. And then really your inputs are simple. So in this case, you put in the room height of the space that you're looking for. So we said it's a patient room with a 10-foot high ceiling. You put in the density of people. So when there's only 4 people in there, each of them has effectively 310 square feet. You put in the amount of time that they occupy the space, 24 hours. And then you just put in a reverberation time. How echoey, how hard, how soft is the space, just so you can do the acoustic analysis. Other than that, on the far side, you're just selecting the risk factor that you're interested in, whether that be 0.5, 1, 2, etc. So from that, you start to get risk data appear. So we have a 1,240, so 1,250 square foot room with 4 people in it. So our done check is that correct? The right size of space, is the number of people correct? If something's wrong, we do the numbers. I've chosen 0.75 as an air change rate. I know we were actually only at 0.58, but let's just assume they're delivering a little bit more air than they were. Under that condition, we have a relative risk of infection of 2.9. So with not enough outside air being delivered, one of those 4 people or more have a 2.9 times chance of being infected than had they been at home. To overcome that, we want to be down here. So in simple terms, if we can increase the outdoor air content to 2.25 air changes, at that point, you don't need any internal filtration. You don't need UVC, you don't need bipolar, you don't need to add anything. At the end of the day, the best thing we can do to kill COVID is to increase the amount of outdoor air, clean the room up as best as possible. So I always offer this to people as, look, I'm not trying to sell you something, I'm just trying to show you a way where you can prove that the engineering measures you do are having an effect against COVID. So obviously, if your system is capable of ramping up from 156 CFM of outdoor air to that room to 464, at that point, I think you're wasting your money putting any other measures in there. Put them in if you like. But this is your best way of reducing risk. And obviously, if you want it at 0.5, you're going to be somewhere down here and it will take you there. But if your system was really designed for this, you might be able to double it. It's pretty uncertain that you're going to go 3 or 4 times that amount. Otherwise, that system was heavily over-designed. And please bear in mind, you're now bringing in a lot more outside air. So that's outside air that in the winter, well, you don't have them here, but in the summer, you're going to have to cool down to 55 degrees. So that's a big energy spend, but it's cleaning up your space. If you want to go UVC, all we've done then is attached a product that we make and said, right, based on that criteria, based on the performance of the piece of kit, the equipment, this is how many you need to apply in that space. So it's not, as I've seen, a lot of manufacturers' data sort of says, this is kind of good for 600 square feet. There's no how many people are in there, there's no how long are they occupying. It's like, here's a box, and in our opinion, it should be good for 1,000 square feet. So we wanted to put a little bit of science behind the application of, if you like, a product that we're promoting. And it'll even tell you what the combined noise level is of having 3 units in there. And by the way, hey, look, if you could go from 3/4 of an air change to 1 air change, just a slight tweak, you can go from 3 units to 2 units. You could save money. So what we're trying to do at the moment is give you a program based on a white paper that's analyzing risk, that gives you solutions that you can apply before then you start to buy other measures, such as increasing the filtration, going from an 8 to a 14, adding a room in recirculation. So this should be your starting point and something that you go to the hospital or the university or the school or the gymnasium or whatever it might be and say, look, there are measures that we can take to start with, and then based on how far we can go and how much money you want to spend on your bills every year, we can then apply other technology. So just to move that on, this is now, sorry, that's where we were, 2.9 times the infection rate. Now let's go to 12 people. So all the visitors are in that space, all at the same time, and they are there now for 8 hours. So I've changed from 24 to 8. I've decreased the area to get it up to 12 people in that space. Believe it or not, the risk of infection is about the same. What that's telling me is the time is a very, very big factor in that. And so if we then say, well, okay, now let's look at 12 people in that space for 24 hours. Wow. Now we're at 8.4 times the risk. What's going on? Well, someone's got COVID and they're breathing. And that COVID is floating around in the space. In fact, COVID tends to be driven more by buoyancy than airflow direction. So over time, that space is becoming more and more infected, to the point that the outdoor air you're putting in and the air that you're sucking out isn't removing it and it's growing. So in that case, based on that time, well, look, I'm up to 4 air changes and I still don't have a solution. So as I said to you before, when selecting outdoor air, you've got to look at the total time that they occupy the space, not just per hour. It's quite a significant factor. So I've also done a crib sheet on how to use the selection software. So Anybody that wants it, we will send it to you. As I said, it's an Excel spreadsheet. You'll get it from Humera. It'll come with the crib sheet. It'll come with the original German paper and the translation of the German paper. So you can then study it at your leisure. And then just to show how these parameters affect the result. So we want to make everything that we go to, let's say, at least have the same risk as our safe harbor. Okay, so slightly different scenario, an office space, 12 people, they've got one air change of outside air. So that's not the total air that's being delivered, that's purely our ASHRAE 62 requirement. Okay, so we're delivering 180 CFM of outside air. 12 people in the space, start at 8 in the morning, go home at 4 o'clock in the afternoon. So 12 people, one air change of outside air, and obviously our risk factor on that is we got 2.6 times the risk than had we been working from home. So what can we do about it? Well, let's double the outdoor air. Okay, well, as you can imagine, by doubling the outdoor air, the risk is halved, but it's still 1.3. So at some point, we have to go higher. And in this case, if we get up to 2.5 air changes, so we've gone from 1, so we're now 150% higher, 250% total, we can now get our risk down to 1. However, we've increased our running costs all year round. We could say, well, let's reduce the number of people. So let's put half the number of people in the space. Okay, back to the same thing. 6 people in that 1,000 square feet space. Our risk factor is 1.3. What does that mean? We have fewer staff. I know some companies now that have totally given up having an office space. Everybody works from home. There are other companies that still have a problem with that, so they're making people come back to work. But ultimately, you've got fewer people in the building, that building that you're spending all that rent on. And if you get down to only being 4 people in that space, do you know what? The outdoor air that you were delivering was perfectly adequate for that space. Or, hey, let's reduce the occupied time. So let's start at 10 and finish at 3. What does that mean? Still got a higher risk. So now we're working less hours, I would say, fewer hours, but reducing our risk. And in fact, if you get those 12 people to only occupying your space for 4.5 hours a day, your risk is back to 1. So the idea behind the tool is you can play with your parameters. You can say, okay, I can't up the airflow too much. Maybe I can go up from half an air change to 1. So what can I change? Well, I can have fewer people in the space, or they could occupy the space for a short amount of time. So in a way, we've almost been doing a lot of these features automatically. The restaurants where only every other table is now available, or they have limited time available, are doing that same thing. So in this case, wow. What we also show you is, okay, if you add a UBC product, our product, you can get that safe harbor down to 1. And that way you can fully occupy the space. You have all your staff levels. You're utilizing all that dollars per square foot that you're paying for that wonderful building. And then you can add more units and you can totally reduce your risk if that's where you want to be. So let's look at their recommendations and also ASHRAE. Hopefully some of these might strike home, but do not trust the ventilation rates on the VAV system. If we're bringing in fresh air here and we have a number of terminal boxes that are open up or closing, guaranteeing 13 or 14 CFM a person from that final diffuser is probably impossible unless the job is running at 100%. So that's particularly nasty. Avoid recirculation systems. Try not to redistribute your air from one space to another. Do not assume you have a fully diluted space, and I always give the the example of the Cube Farm. So, you know, these are those very nice people that ring you up saying your car insurance is about to run out. I like it when they give me a call. Well, as you can imagine, if you're ventilating that space and you're ventilating from high level, as they do in a lot of these boxes, trying to get 15 CFM per person or 12 CFM per person to every person isn't going to happen. So even the layout of the structure can seriously affect your distribution. And if you think that's an extreme, well, we tend to see this all the time. And all of that has the same impact. Use displacement rather than mixed flow systems. So bring the air in at low level. Ideally within that Cube Farm, have a floor outlet in each cubicle so that everybody's getting their 13 or 15 CFM per person delivered directly to them. Under displacement, that air is going to rise over their body. It's going to take out what they're breathing, take it up to high level, and then it will be returned and taken away from the space. Really, the conclusions of the report suggest that if you cannot increase the ventilation rate delivered to the space because you have lack of capacity, because increasing the airflow is going to make it too noisy. If you're doing a school, typically you're bringing in 400, 450 CFM to a classroom, and you've now got to get in 600. It's probably going to be quite noisy at that point. Outdoor conditions. Well, if you're living the dream in Southern California, other than the dream is it often appears to be on fire, there's no water or whatever. So opening windows isn't necessarily a great solution for you. And obviously there may be safety concerns if you're in a high-rise building. You don't necessarily want a lot of open windows that people could fall out of. Then in that case, the influence of air filtration within the space, as well as the effectiveness of UVC, should be used. Bipolar is not allowed in Germany. It was banned about 20, 25 years ago, because a lot of the older systems did generate ozone. Now, my understanding is all of that has gone, but obviously in Germany, in the middle of a healthcare crisis, if you go back and say, by the way, you think bipolar is a good idea, they're probably at that point not going to change the rules. So it doesn't appear as an option within the German paper on the effectiveness against these airborne viruses. We also are not a lover of filtration within the space, mainly because COVID could survive up to 24 hours on cardboard and 5 days on paper. And most MERV 13, 14 filters are mini pleated paper. So if you then expect your maintenance guy to have to come along and take out this basically contaminated filter, how are you protecting it? So these are these low-level MERV 13, MERV 14, I call them Daleks because I like Doctor Who, but these are sort of square boxy things, typically about yo high. They suck in air at low level and they distribute it back to the breathing zone. Now, in terms of COVID, everything that falls to the floor is great. It's going to die down there. What we're really interested in is what's going on within the breathing zone. So I don't want to be sucking stuff off the floor and blowing it out sideways. I don't want what I'm breathing being aimed at the person next to me. So in my opinion, these are a really very good solution. If they were pulling in air from the breathing zone and redistributing it across the floor, it might be a good solution. They're heavily compromised by obstacles and furniture. So you then got to think, where am I going to put this? If I'm trying to protect you and I have this box over there, how's that going to protect you from all the people between you and it? So we feel that a high level UVC solution without a filter overcomes these issues. And therefore we're an advocate of something mounted centrally within the room, which is just a room scrubber. It needs a power supply and that's it. It's not hooked into the HVAC. You probably put it into the lighting circuit so that when the lights are on, it's on. If we were in here, I'd probably stick 2 of them in here, based on maximum occupation how long you're likely to have a meeting, and how much outdoor air is actually being delivered. So in terms of the ASHRAE position document, when they talked about healthcare buildings, said provide 100% exhaust from patient rooms, do not recirculate air back to that patient room. Therefore, people that are putting in better filtration by the air handler or UVC by the air handler are doing nothing in the room. All you're doing is cleaning outside air. You're not cleaning any recirculation, because in their opinion, there shouldn't be any. Use UVGI or UVC, and they have 5 levels of evidence. So evidence level A is it's been used a lot. There's sound evidence that UVC works. There's sound evidence that it works in these type of applications. Going through to evidence level E, which is kind of, if you try it, good luck. Believe it or not, bipolar again doesn't even feature on that list. It's not on that document at all. Personal opinion of why bipolar doesn't work. Okay, the way bipolar works is it turns some particles positive and some particles negative, and they clump together. And by clumping together, it's easier for them to be sucked out of the room. That's great if you're removing dust. The problem with COVID is the more particles you breathe in, the worse your effects to it. So if you've got something that's clumping COVID together, and it's there, and I'm here, and it's coming at me, the chances are I'm going to be breathing in more COVID particles. So that's a personal opinion of why I don't think it's a great solution. And increase your outdoor air from 2 air chambers to 6. Again, it's back to the simplicity thing as, well, let's just do that. What we've tried to do is show you where you were and where you're going, and is that enough? In that four patient room with 8 guests, is that enough to still be safe? So let's look at UVC and how and why it's applied is critical. So why UVC? So this is our electromagnetic spectrum going from radio waves to radioactivity. And as we know, the shorter the wavelength, all the way up to the far end, the higher effect it has on a human being. So, side story. My wife loves analyzing things for health. And there's a thing on Groupon that you can buy where you send in 10 hairs, and eventually you get this report back of all the foods you can eat, all the foods you shouldn't eat, all the things you should drink. And amazingly enough, for us, when we got the reports back, the things that we should eat typically were the things we didn't like. My wife hates milk, she hates onions, and in this report it says she shouldn't drink milk, she shouldn't eat onions. I hate garlic, yeah, it came up as I shouldn't eat garlic, so it was good. It also showed you what metals you have in your body and whether they're toxic or not. And I suppose what I'm getting to on this is my wife ended up having plutonium in her body. Now I kind of looked online as how do you get plutonium in your body? And evidently it has to come out of a nuclear reactor. So what I'm not telling you is my wife was actually born in Ukraine 2 years before Chernobyl went up. So as a 2-year-old child, at some point she breathed in a speck of Chernobyl. And I sleep next to Chernobyl every night. I think I'm safe. I think it will probably have a long-term effect on that, but that's just radioactivity. So if we look at the visible light spectrum, to the right, to the shorter wavelengths, we get the ultraviolet spectrum. So just to enlarge that part to here, it runs from 400 nanometers down to about 150. And just to break it up into its 3 constituent parts, UVA. For those of us that are old enough and remember discos, this was that crazy light that used to light up everybody's underwear and make you what we call a black light. UVB is what we spend hundreds of dollars every year trying to get sunburns, but it also gives you skin cancer. Both of these naturally hit the Earth's surface. UVC is absorbed and reflected by the Earth's surface. The big concern over the hole in the ozone layer was it would allow UVC to come to the Earth and burn the planet. So UVC kills microorganisms by locking up its genetic makeup. So in terms of COVID, it stops it breathing. And a live COVID particle can float around in this space for about 14 to 15 hours before it naturally dies. So the idea is we want, and it's doing it because it's constantly replicating. So in terms of UVC, it stops that process immediately. In terms of best absorption level, it's around 260. Most UVC products are here because that's about the peak output for a effectively low-cost mercury lamp. There's been a lot of talk now of shorter wave UVC down here, down in the 220s, but again, moving up into the more health concerns you should have within the space. There is a big difference between having a big lamp here in an empty room or having something where the room is occupied by people. So in terms of the advantages of UVC over other solutions, activation happens immediately. It locks up its genetic makeup immediately. There is no immunity over time. It cannot build up resistance to it. And obviously its effectiveness is based on its dosage, its degree of disinfection. So in terms of COVID, we actually need 120 watt seconds per square meter to kill COVID within that space. The good thing for us is that's also sufficient to kill flu, airborne pneumonia, or even airborne E. coli. So we're not just dealing with COVID now, we're dealing with, and we're starting to get into the silly season now, so obviously flu. The big concern, certainly over my side of the country, is RSV, this thing that's affecting all the children. And the reason a lot of the hospital beds are now being used up is a combination of those three. And if your kid is under 4, it looks like it could be very, very bad. Beyond that, seems to be better. I'm not sure how RSV is being distributed from child to child, but I'm guessing it's going to be airborne and contact, probably at schools. So we've got that concern. We still don't know what the next outbreak or the next variant of COVID will be. I think it's going to be here for some time. I think it's going to be a regular shot like we have with the flu. It's just like everybody's bored talking about it now, and everybody wants to get on and have a life. I still would like murder hornets to come back. They had very little impact on the world. There was this huge threat that they would wipe us out. They never did. Maybe next year. So in terms of the dose, it's a factor of how bright, if you like, the radiation intensity of the lamp and how long it's exposed to that lamp. So there is a world of difference between killing COVID in a petri dish and trying to kill it when it's in a moving airstream. And the reason I point that out is everybody tends to quote, oh, we got a kill rate of 99.99. We've tested it, blah, blah, blah. Yeah, we've held a lamp over COVID suspended in a gel. It can't go anywhere. We've done it for 2 to 3 seconds and hey, voila, it's dead. Therefore, as long as we do the same thing, everything else dies. Well, when it's in a moving aerosol, what you need to do is attack it from all directions. Why? Because your dwell time is very, very short. It's not 2 to 3 seconds. If something was recirculating there at that lower rate, I'd kind of give up. And by the time it killed something, I would have got to the toilet, come back, had a beer and put the feet up. So what we've done, and I hope what a lot of other people do, is they actually build what we call a radiation chamber within the product itself. So In terms of product design, sorry, I'm talking about that. Some mechanism to bring the air in, maybe with COVID. Light baffles, incredibly important. UVC should not escape the product. If somebody brings a UVC product to you and you can see blue UVC light, turn it off immediately. Some form of radiation chamber where it deactivates the virus, and then additional light baffles before it comes back. So in terms of something we're promoting, where the light is, has no outside edge that it can break out of. So this is within our product, the radiation chamber. It's actually only that high. Everything you see is reflection. And why are we doing that? Well, COVID with air is coming past here at about 0.3 feet per second. Okay, light evidently is going at 186,000 miles per hour, almost a second. So we can bombard these particles from 360 degrees around the globe. We can make sure it's dead by the time it comes from here to here, and we can make sure it's dead anywhere within that chamber. So, sterilization. In-ceiling unit, certified to be hazard-free operation, to have no light breaking out of it, no UVC light. The limit is 0.219 BTUs per square foot. In terms of this, if you sit eight inches away from it, staring at it for 8 hours, you won't get to the maximum dose. Lamp lasts 5.5 years. Lamp has been independently certified to kill COVID in a petri dish, because that's all you can do. And meets UL 2998, it's an ozone-free technology. In terms of testing, because we test every single one, the maximum limit is 0.219 to be seen as safe. We're at 0.00004505. So yeah, it's safe. And the reason that came up, I was dealing with a very large university. They wanted to put a lot of these in. They asked us how much UVC escapes our unit. The competitors said it's negligible. And we said, and they said, well, what does negligible mean? And none of them could define it. So we actually defined it and said, here you go. That's what you can extend. Oh, just hours of operation. We also did some testing, so you can go to LinkedIn. It shows you a before and after space. So the chamber didn't have the recirculation unit in it, and then the chamber did. And what we showed is the way that it cleaned up the breathing zone. This is effectively our unit producing COVID, and it's still producing it. It doesn't stop that person being infected. It made sure that in this zone here, this is where we stay clean, which is really what we're important. And then if you're going to stick an exposed unit, we always recommend you put them at high level, you put them on a table, or you mount them on a wall. Why? Because I want to be sucking air into the unit. I don't want to be sucking air into the floor. And then typical sort of applications. This is a dental surgery. They put it on the floor, thanks. Gymnasium, they stuck it up on a wall. And summary. So the idea behind the model is it allows you to predict the effectiveness of the current outdoor air you're delivering to that space. From that, you can understand the benefits of increasing outdoor air against the budget. How much does that customer want to spend per annum, increasing his energy costs to reduce his risk? You can then apply a long-term solution, whether that would be increase the outdoor air, add UV, add MERV filters, add whatever you want, and then to end up with an enhanced current and future protection for the occupiers of those sites. And I'm done. Other than, do you have any questions? Somebody's screaming.
Just on the average, the size of that product that you have on the screen, what are those dimensions?
So this,
I'm sorry.
so the in ceiling unit is a tile replacer, 2 foot by 2 foot, 8 inches high. And then a freestanding one, which I think is totally over designed, but that's Europe for you. Nice curved edges, whatever else. That's it. And the only difference between that being on the floor and on the wall is we actually we sell you a bracket that you mount on there. You pull the cable through, you mount the unit on it. End of story.
How much flow are you circulating?
So anywhere from 50 CFM to about 170. We normally set them at 120 because we want them to be super quiet. And again, the problem I have is they're too quiet.
You have an ECM motor?
Yes, yes. Yes, sir.
Is it, first question, is that intense, so you can just pop out of that? Or
Yeah.
it doesn't have to be reinforced?
8 inches high, 4 hanging brackets, connect the power to it. So totally independent of your HVAC system. It's basically saying you've increased the outdoor air as much as you can. How do you add something on top of it? And I always argue with people, if you're increasing the outside air, but you've only got one return grill, you put the supply in here, you put the return over there, all of this air has got to go that way. So I want to sit under the supply grill. I don't want to sit under the return air grill. And as I went back before, probably in here, maximum occupation, if it's only 2 hours, you probably get away with 1 unit, but maybe 2 to be sure. If it's longer presentations, then that's when you start talking about it. Some people put them on timers, so they say, okay, let's have a PIR that sets people coming in, turn it on, and then when the last person's gone, let's let it run for another hour. You can put them on a 0 to 10 volt signal, so you can actually increase the flow rate. People will say, okay, the room is now unoccupied, let's go to maximum flow for half an hour just to purge the space before we turn it on.
Parameters like pressure and humidity determine the effectiveness.
They're going to affect the move. Well, yes, but we haven't got anything built into here. Yes, I suspect. What I don't know is how that affects the amount of particles that are within the air itself. All we're saying is whatever passes through it is going to be 99.99% dead. We're not actually adding any pressure to the room itself. You're talking about how far above sea level we might be, and therefore the effect on air of that. Yeah, I know it affects like heating and cooling capacity, but I just don't know how it affects this. You're the first person to ask that hard question, but I will ask the question.
You mentioned reverberation factor.
yeah.
What effect does that have and how do you determine it?
So normally the engineer will know what that is and he'll set it with the architect. But it's a little bit like the last time you moved, when you moved all of your furniture out your space and you took up the rugs, that became a very hard space. It started to echo, reverberate. The worst examples tend to be the classic old railway stations, where the tannoy is going and you have no idea what it's saying, because the reverberation time is so long that you're hearing multiple messages. An average space typically should be below about 1 second. So an office like this should be less than 1 second. If it's over 1.5 seconds, it's hard to have a conversation with them.
Right. Well, what effect does it have on
It's not on the kill rate, it's purely how noisy the product is.
oh, okay.
So we assume a certain room attenuation, and then we say, what is the reverberation time? Because even if I've got something quiet, it's in a very, I don't know if any of you had problems, but you do, let's say, a design for a lab where it's lino floors and glass walls, and all of a sudden everybody says that system you've been designing for years is noisy. It's because you've got no room attenuation, you've got no soft tiles or rugs, you've got no barriers to noise. So it's the same thing with this. If you don't know what the room attenuation is, sorry, the reverberation time, how long a noise echoes, its finger in the air is really how noisy it is. And again, I work for a German company, so they like things to be less than NC 29. And that's why I always say these things are probably too quiet for the US market. Only because, okay, don't take this wrong, but in Europe, if you can't hear it, if you can't feel it, and if you can't see it, it's working. Here, unless you can feel it, unless you can see it, unless you can hear it, it's not working. You know, I go into a restaurant in Georgia, and the air is blowing so hard I have to wear a coat. And I'm thinking, this is air conditioning? No, it's cold in here. So it's the sort of same thing. I did some jobs in the Middle East years ago where we had to attach little bits of tinsel to the
Yes.
fan coils so that the local Arab gentleman knew the thing was working because they're used to hearing it, you know. Or we're used to staying in hotel rooms where there's a PTEC and we're used to that buzz noise as the thing starts up. You know, there you go. So yes, these things are very quiet and we want to know how alive the room is to determine the effects of 1, 2, 3 or more in a space.
Okay. Anyone else? All right. Well, thank you very much, Chris.
You're welcome. Thank you very much.
Can we switch
Yep.
back here
Okay.
and we have a little bit more to cover?
Do you want the camera on as well?
Sure. Why not?
Why not? Should be. Yep, camera's on. I don't think you can see it, but the camera's on.
And where's my previous?
Oh, sorry, you wanted the other thing?
Yeah, before there we are.
So let me share that. Put the glasses back on. I don't know why I took them off. There you go.
Excellent. Okay. I have a couple more things to cover here. Some coming events. The CSHI Los Angeles chapter elections are coming up. The nominations have been submitted. Nomination period is closed. It's now in the hands of the nominating committee at CSHI. The ballots should be sent out sometime in November. I believe there'll be a 7-day voting period once the ballots are sent out. So watch out for that email. You should be receiving a ballot in the next few weeks. And coming up in Anaheim is on the November 9th and 10th, the Natural Disasters Expo is at the Anaheim Convention Center, including presentations on heat and fire, floods, storms, and earthquakes. All the good California stuff. And this year's expo will feature our own Santiago Chambers, CSHI State Vice President, and Anthony Crawford, the president of the Northeast chapter, will be speaking there. And free tickets are available to CSHI members. In the e-bulletin that came out on the 18th, there's a link to get your free tickets. The link is also available on the CSHI website. Under the news tab, you can find this e-bulletin. And now coming up, Alan is going to be providing us with some deep fried turkeys again. This has become somewhat of a tradition with the Los Angeles chapters. We have a potluck for our Thanksgiving dinner. And Alan has graciously volunteered to cook again. We'd like everyone to bring some sort of a holiday dish. The exact time and location of our potluck should be determined shortly. We're also planning a chapter holiday party in conjunction with the Orange County chapter. And we'll give you more details when we work that out. If anyone is willing to help in putting together either the potluck or the holiday party, please let me know. Or you can reach me through Beth Demeter at CSHI. As a member of CSHI, you're not limited to participating only in the LA chapter events. You can attend other chapter meetings and events. For those who are willing to go to any lengths for a party coming up in December 2nd is the Northeast chapter holiday party in Sacramento. And in San Francisco, the holiday boat cruise will be December 7th. Okay, you can find details on these events and sign up for them on the CSHI website. We are looking for places to hold in-person meetings. If you have a facility that can accommodate 50 people that we hopefully will get back to again, as that was our typical meeting size before COVID. We'd like to hear from you. If you have a facility in LA or Ventura County, the LA chapter includes Ventura County, please contact Beth. And if you have any suggestions for a presentation, let us know. We want to hear from you. And finally, there's Beth's contact. One more word on COVID. You may have heard that Governor Newsom has announced that he will end the state of emergency on February 28th, 2023, exactly 3 years after he declared it. That will start the clock counting for us in healthcare facilities for the time that we have to undo all the unapproved changes that we made, that OSHPD and now HCI allowed us to do when the regulations were suspended for COVID. For some of us, undoing all that stuff is going to be a tremendous task, and we need to move ahead aggressively starting now. Okay, that's the end of my online presentation. Thank you all, our Zoom audience, for tuning in. We do have a few things more to do here in person at Diamond Bar, but I can give you back a little more time for your day if you're on Zoom. Thank you, and I hope to see you in person at our holiday potluck dinner. So, thank you very much.
Thank you, Phil.
Okay. And